Okay, so let's start with today's topic. So classes are going to be shorter now because of Ramadan. So today we are going to talk about, let's start with the ideal gas, but not in the canonical ensemble, but in the grand canonical ensemble. And why is that? So can someone tell me what's the difference between the canonical ensemble and the grand canonical ensemble?
The grand canonical ensemble considers variable volume.
Variable number of particles, not volume. You can have variable volume both in the canonical ensemble, but then grand canonical ensemble, you can have variable number of particles. Okay. So if I have a partition function in the canonical ensemble, so this is the n particle partition function, say in the canonical ensemble. So this is depends on the volume, it depends on the temperature, and depends, say, on the number of particles. So to go to the grand canonical ensemble, we multiplied with e to the power beta mu n, and we just add a constant term so that we can write it like this. So this is the grand canonical ensemble. And because, we have a factorial of 1 over n factorial here, remember that Zn is Vn n factorial lambda 3n. We can express the grand canonical ensemble Z tilde as an exponential. And in the exponential, we have e to the power beta mu v divided by lambda q. Okay, so this is a power series. Now, one thing we want to do is that we want to compute the equation of state of this gas. So why are we doing this? Let me just tell you why. So suppose that this is a gas and it's inside some container. So the number of particles is fixed. So, it's appropriate to express this in terms of the canonical ensemble. But suppose that you have a smaller box, still quite large, an imaginary box inside your bigger box of gas. So the average energy of this smaller box of gas, this is, so this smaller box of gas is going to exchange energy with its environment, right? And because it doesn't have any rigid walls, it's also going to exchange particles with the environment. So the number of particles, the average number of particles inside the smaller volume may change. So if you want to understand, such a system, which is a subsystem within a bigger system, you should consider the grand canonical ensemble. So this is the motivation for looking at the grand canonical ensemble. Okay, is that clear?
So from micro to grand canonical ensemble, we're basically taking into account more variables. Is that right?
Yeah, the micro canonical ensemble you had. Sorry, the micro. The micro canonical ensemble. You had the energy of the system fixed. But we see that for more general purposes, we need a description where the system can exchange energy with this environment, right? And that's why we went to the canonical ensemble. And the grand canonical ensemble is when, yes, the energy can fluctuate, but so can the number of particles. So microcanonical ensemble is very, very restrictive. Okay, so
did we do canonical ensemble last time?
We did both, I think. Yeah.
So are there any more canonical ensemble after grand?
Yeah. There are more. I think there's the pressure ensemble. There are a few other variations, but for most purposes, I don't think we don't need more than these three. I mean, you can come up with your own ensemble which is applicable in some situation, right? I mean, so, but for the rest of the course, we won't need any other ensembles. Okay. Yeah, Saif, if you go back, you look at the lectures, you'll see that.
Yeah. I went and read it. Yeah, it is canonical on the last one.
Yeah. I mean, okay. So now that we have the partition function of the grand canonical ensemble, we can calculate what the equation of state is. And if you remember, the grand canonical ensemble had a very nice potential, which was called the grand canonical potential. And that potential said that if we could compute that potential, then that potential would give us minus P times V. Okay, do you remember that? That was a nice thing about the grand canonical potential. On the other hand, the grand canonical potential is just the generalization of the free energy in the case where we have the grand canonical ensemble, right? So it's essentially given by minus kBt log of z tilde. And that's just minus kBt e to the power beta mu v divided by lambda cube. And we see here there's a factor of v. So we can write this as minus kBt divided by lambda cubed e to the power beta mu times v. So this tells us that this is nothing but P. So P times V is kBt e beta mu by lambda cube times V, right? So, but on the other hand, we also calculated what the number of the average number of particle n is. And it's conventional to call this average number of particles n, okay? Although n is usually just the number of particles, not the average, but it should be contextually clear which one we mean. So this thing is, if you go back, we worked out that that's going to be kBt del mu. Well, it's also not very hard to see. The log of z tilde with respect to the derivative of log z tilde with respect to the chemical potential. So if I do this and I apply it to the, we work out what the expression for n is. Well, we just essentially use this in this equation. Then what we get is PV is equal to KB Tn, or Kb n of t. Okay? So we see that the grand canonical ensemble also gives rise to the same ideal gas law as we derived using the canonical ensemble. Which should make sense, right? Because all we are looking at is a subvolume of our ideal gas, and we are still in the classical regime. We are not, like, this volume is not so small that quantum effects should be kicking in. So we should expect the same result, and we do. Okay?